Flow, teste. 1, 2, 3. O estudo de estruturas de dados. Dá pra me ouvir ainda? Eu tô virado pra trás. Você falou que era ruim. Dá pra me ouvir ainda? Eu tô virado pra trás. Dá.
Posso aumentar um pouco que tá no máximo.
Que é? A, B, C, D, E, F, G, H, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. Tá tudo certo? Falando que nem o abaca. Então, eu tô indo para longe aqui da tela, vendo se está funcionando, indo para o meio aqui, virando ao contrário, dando uma pirueta. Parece que funciona bem, só o áudio do X fica alto. Quê?
É que eu ia marcar. É tudo? Tem uma consequência de ruído aqui embaixo, camiseta na cabeça.
Eles ainda fazem isso?
Espero.
Eles parecia que estavam querendo parar.
Eu quero meter-me no meio e editar. Ah, cadê bom?
E aí?
Já apontou pro cara que ele é seu arqui-inimigo?
Não, ele não é.
Quando que vai ser essa grande revelação? Você tem que desenrolar a ao longo da semana, eu acho. A gente devia assim só mandar o link por e-mail pra ele, tá ligado? Ele não vai saber o que aconteceu.
You couldn't connect to Ian? It doesn't show up?
It shows up but when I doesn't show up right now. Sometimes it doesn't, sometimes it does.
That's weird. Which ones are USP Code Lab? Será que esse USP Code Lab é aberto? Vou perguntar pra eles. We know these guys. Let's see if they have an open.
A Cida bendiga.
Ah, o
Tudo bem? O instalado.
tem um computador mais usado? Tem um mais
Ei, pelo menos isso daí de orgulho. Você viu?
Alô? Alô, alô, alô.
Tá certo?
Parece que não, né? Porque o Ian tá parado ali e o Ian não tá aqui. Ó, tá no pause. Ó, a entrevista aí.
Alô?
Esse microfone vai dar umas cortadinhas.
Vamos.
No outro chat. Me passa o link.
Tá no Facebook. Tá no Facebook. tá sem som. Xinga ele.
Tá com som sim.
Aí, Carlinhos.
Tem som!
Você deveria estar ouvindo aqui esse grito.
Tem som!
Agora
Testando,
vou desligar.
2.
All right. Does it work? Not really. Oh. Does it work now?
I think that, yeah, now it's working.
Now? Yes. All right. So let's try if it works normally now. Does it work now?
Yes.
Can you hear me? All right.
So, hi everyone. Just to make some announcements, every day lecture will be in this room. The content will be on our labs. That's in this building. For the contest, everybody needs to have a CF account. And I think that's all. Well, I present to you Jakub Safin.
Hello, I am Jakub.
Yeah.
I will be a lecturer. Yes, regarding that code forces account, it's, for those who don't know, site is codeforces.com, and we'll have contests as mashup contests in the Codeforces gym. So these are special; they can't be seen normally, and you need to send me. You need to make an account either for everyone individually, and then make yourselves a team, or just make one account for the team and then you'll compete from that account. Anyway, you have to send me your account name to this username, so I could register you for the contest. It's not in a hurry, just before those contests. The topic we will have today, because there is no problems to explain from previous contests, the following lectures will be always about explaining problems, and then if there's time left, then maybe something else. I have some smaller topics prepared, but for today there will be one bigger topic, and that's power series, polynomials, and everything related to that. In general, basically we'll always deal with today either infinite sums or polynomials where k equal 0 through n. Polynomials like this of degree n. First of all, well, let's talk about one topic which is quite common in modern programming contests, although it wasn't very common a few years ago, which is Fourier transformation, or computing convolutions, because that's basically the only thing we use Fourier transformation for in contests. So let's say a general problem where we have A1 through n and B2 through m in general, and what we want to compute is an array C1 through m, where each Ci is a convolution, so it's a sum like this one, where obviously j is from 0 through I. So when we want to compute the ith number in this array C, then we take, right, I should probably use indices from 0. So from 0 to everything. When we want to compute Ci, then we take Ai times B0. This should be 1 also, 1, 2, and so on. So Ai B0, Ai minus 1 B1, etc. And we want to compute all of those numbers, n plus 1 numbers, which is obviously too slow when we do it just by computing this sum, because it's n plus m times O n plus m, which is O n plus m squared. Here is where the Fourier transformation comes in. Because let's take some new arrays. We'll transform this array into an array big A 0 through n, and this array to big B, uppercase B 0 through m. Zero through, right, this will be n plus m. I'll get to that in a while, that these arrays need to have equal lengths, but this isn't very important right now. It's just that. We get to the power of minus ij aj, and same for b. bj. These are the formulas with small a, small b. These are the formulas we use to compute the elements of these two arrays. This is a Fourier transform. When we don't have minus here, then it's an inverse Fourier transform, and it works like the inverse should, that if we apply the Fourier transform to this array and get this array, then if we apply the inverse Fourier transform to this array, then we get this array back. So A I equals the sum of basically the same thing, just without the minus. Here, let's deal with the lengths of these arrays, because for the Fourier transform to work properly, there are various versions of it. By I minus j is at least m plus 1, so we only multiply zeros here if I is greater than n. So if we compute everything up to 2n here, then this will just be zeros, but is necessary so that the algorithm would work nicely, so you wouldn't have to deal with some special cases. So here I'll write 2n, right, 2n, and also we can just take n equal to the power of 2, so that 2n would also be equal to the power of 2, because if we have arrays like this with lengths equal to powers of 2, then the Fourier transform works very nicely. It can be done as a fast Fourier transform, which I won't explain here because it's way too complicated and you don't really need to know it. It's something you copy always in contests. I don't really remember how to implement it, just know roughly how it works. You really won't need it. So here we have 2n, where n is equal to a power of 2. Let's say lowercase n. And now I can write the bounds here. I is 0 through n. N. What do we do with this? There's something you may have heard of, the Convolution Theorem, which says that if we transformed this array C also to an array uppercase C0 through C to n, where the same thing applies here, then we would have uppercase C equal to uppercase A times uppercase as a scalar product. So if we want to compute this array, then we should transform this array into this one, this array, then use this formula to get this array of uppercase C0 to n. And finally, well, we have the inverse Fourier transform. So just like we can get this lowercase a array back from the uppercase A array, just like that we can get we can take this Fourier transform array C and use this formula, use the inverse Fourier transform to get this array. The time complexity of computing big A from small a, or big B from small b, or small c from big C is always O n log n. This is the well-known property of fast Fourier transform that when we have n equal to a power of 2, then we only need this complexity instead of O(n squared, which we would need if we use just this formula straightforward. Also, you can notice that this is just a formula for polynomial multiplication, because if we have this polynomial, and write it as a product of two other polynomials, where the elements of array C are coefficients of this polynomial, the elements of array A are coefficients of this polynomial, and the elements of array B are coefficients of this polynomial. Then this is exactly the formula for polynomial multiplication, because where should I write it? The power of j equals the sum of ak bj x to the power of k plus j. So if we fix this exponent of x, this is the sum over all kj. If we fix the sum, then this sum represents I. One of those coefficients k or j represents j in this formula. The other is the sum minus that coefficient, so it represents I minus j. And so the coefficient at x k plus j is exactly c I, which represents this sum, is exactly c k plus j. So Fourier transform and polynomial multiplication are naturally connected. It's also quite common that if you have some problem with a recursive formula that uses a lot of either polynomial multiplications or additions or something like that, then it can be usually solved by some Fourier transforms, and vice versa. If there is a lot of things that look like Fourier transforms, then the result is often a polynomial, coefficients of a polynomial, value of a polynomial at some point, and so on. Since the Fourier transform and polynomial multiplications are basically the same, then we know that multiplication of polynomials is commutative and associative. So this is the same as writing cx times rx, and if we have if you're multiplying multiple polynomials together, then it doesn't matter in which order we multiply them. And the same applies to Fourier transforms, so it doesn't matter in which order we do the Fourier transforms of several arrays, which can be used to make a faster convolution of multiple arrays. So if we need to multiply 3 polynomials, then we can Fourier transform the coefficients of the first one, the second one, the third one, then use this formula to just multiply corresponding coefficients with the same index together, and then the result is the Fourier transform of coefficients of their whole product. And we can use the inverse Fourier transform to get the coefficients of the original polynomial, original product. Also, there's one thing I haven't mentioned. What is this omega? This is quite important because we have all sorts of ways in which we can do Fourier transform depending on whether we want to do it in real numbers. Okay, we have to use complex numbers for it. If we want to take real valued coefficients of a polynomial or real valued elements of an array and then get a real valued convolution, or if we want to do it with multiple prime, it's known that there are special primes in the form in this form, where m is some odd number multiplied by sufficiently large power of 2. Usually we should have k greater than this than n, or 2 power k greater than 2n, so that we could use the fast Fourier transform with this prime. This is known as the number theoretic transform because it uses some special properties of these numbers in number theory. And omega should be a number, either complex number or integer if we want to work modulo that prime, such that omega to the power of n to the power of 2n is equal to 1. Omega to the power of 0 is obviously also equal to 1, but omega to the power of k is not equal to 1 for any k between 0 and 2n minus 1. So I think there should be 2n minus 1 here. But these numbers, omega, obviously exist easily in complex numbers because there is the complex exponential. E to the power of 2 pi I equals to 1. This is an important result in complex analytical theory. So if we take e to the power of 2 pi I divided by 2n equal to omega, I is here not an index, it's the imaginary unit. This is therefore a complex number. Then omega to the power of 2n is obviously e to the power of 2 pi I, so it's 1. And for any other k, then we have omega to the power of k is e to this power, but since k is less than 2n, then this exponent is positive, and therefore complex number, any imaginary number which is smaller than 2 pi I is different from 1. So this omega satisfies this rule. It's not so clear for all of those weird prime, modulo prime number theoretical transformations. But there is one number which is used very often. That modulo, maybe you've seen it in contests, it's some 9, 9, 8, and 6 more numbers after it. I don't remember how it exactly looks, but I remember that if we choose omega equal to 3, then Fourier transform works. That number we need to choose is a generator. There is no way I know to find it easily, but the generators for number theoretical transforms are usually quite small, so we can just brute force it. And if there is some modulo different from the 998 something, and if it's the 998 something, then I'll just I just remember that the number I should use is 3, and you should also remember it. It's faster than looking for it. For now, we'll just stick with complex numbers. Complex numbers have one disadvantage, quite big disadvantage, that they, well, when we use doubles in normal programming languages without some multi-precision, without very high precision floating point numbers, then we aren't able to represent numbers integers larger than 10 to the power of 16 or something like that. So if the result of this operation, if these coefficients ci are larger than 10 to the power of 16, then we lose precision. There are some tricks to mitigate it with splitting these arrays, splitting these numbers into like numbers in a smaller basis, where the basis is approximately the square root of the modulo, if we want to take these numbers modulo something, and don't transform because it's not suitable for all modulos. But it's quite complicated, and it's also something that you should try to avoid. One way to avoid these weird things that use reals to work modulo something is to use Karatsuba algorithm, which is slower. It's polynomial multiplication in O n to the power of approximately 1.4 or something. It's the 2-based logarithm of 3, which can be computed as logarithm of 3 in any base divided by logarithm of 2 in also that same base. And the point of this algorithm, Karatsuba, is to multiply two polynomials just like FFT, but it can be done basically in any type of numbers we want, whether it's integers modulo some number, not necessarily prime or anything, because it just uses additions and multiplications, and it doesn't need some special property like Fourier transforms. So let's say we have two polynomials or two arrays like I wrote there before. Just like before, if they have different lengths, then we can just pad the shorter one with zeros. There's no problem. But let's say they have an odd number of coefficients. This is a special case we need to handle before we can deal with the case where both have an even number of coefficients. So we have a 0 to n. The number of coefficients is 2n plus 1, and b 0 through 2n. We can take C to n, take over n time, linear time, to compute it using this formula, just for I equal to 2n. And since if we have I smaller than 2n, then neither j or I minus j can't be equal to 2n, because they both are only up to I. So C to n can be computed using this formula, and then we need to compute C 0 through to n minus 1. Now the question is how to compute this. We'll split the arrays into two halves. A 0 through n minus 1, a n through 2n minus 1, and b 0 through n minus 1, b n through 2n minus 1. So out of 2n minus 1 coefficients we need for C0 through 2n minus 1, we take the first half, the first n coefficients into this part, the second n coefficients into this part, the same for b. And it's simplest to look at this as splitting a polynomial like I wrote here, where b has coefficients c, r has coefficients a, and c has coefficients b. Then it's like splitting into two polynomials. where R1 has coefficients these, R2 has coefficients these. We can see that when we had ak x to the power of k, then when k is less than n, then R1 just has the first n coefficients for k equal to 0 to n minus 1, and when k is greater or equal to n, then we subtract n from it, and what's left are the coefficients of this polynomial R2, and the same thing applies for these two. So R1, R2, S1, S2, and what we want to do is multiply these two polynomials, which means we take n R2x S2x plus x to the power of n times this part times this part plus this part times this part plus this. Okay, we have some 4 components of this big formula for the product of these two polynomials, and well, we'll split the two polynomials into this 4, so we can multiply these two, and recursively we just find out the product of these two polynomials and these two smaller polynomials. Each one of them has half the length of the original. The question is how to compute this weird mixed product here. I'll erase the arrows since they're confusing. R1 S2 plus R2 S1. The trick is to notice that if instead of using these formulas where R2 and S2 are multiplied by a power of x, if we use R1 plus R2 and S1 times S2, then the product of these two polynomials is equal to, well, this R1 S1 plus R2 S2, we will do x to the power of 2n plus this. And we've already computed this. So to get this, we just need to multiply this polynomial with this polynomial, and subtract this, and we get this. It doesn't seem like we've helped ourselves so much, but the point is that instead of just 1, 2, 3, 4 polynomial multiplications, we computed 1, 2, then the third here, and the rest is just additions, multiplications, and shifting multiplication by x to the power of something is just shifting the array of coefficients to the right. So these are all operations that take linear time. It's no problem to use them. So instead of recursively computing 4 polynomial multiplications, then we compute 3. The time we need to take to compute the product of these two original polynomials with length n, with length 2n, is equal to 3 times the time needed to recursively compute the products of 3 polynomials, each 3 pairs of polynomials where each pair has degree at most n instead of 2n, because we split. Well, for R1 S1 it's obvious, for R2 S2 it's also obvious, and if we add them up, then the degree doesn't change and doesn't increase anymore. So these two added polynomials have also degrees n. So the time needed to compute the product of 2 polynomials where each of them has n is 3 times the time needed to compute the product of 2 polynomials where each of them has degree n, just half of the original, plus On. These are the additions, shifting, multiplication by x to some power, and subtractions. It's all just linear time operations. And there is a theorem we can use to find out how much time it actually takes. It's the master theorem. If I write n half here, then the time this takes, if this is On, or On times any logarithm actually, which is useful in showing that the Karatsuba algorithm takes the same time if we need to do some more complicated operations than just additions and multiplications by a power of x. But this isn't the case here with divide and conquer algorithms. It does happen sometime. If this is just n times maybe some logarithm, then the time it takes is On to the power of this, of log of base this logarithm of this. If this is some b, this is some a, then we need to use this formula to get the time complexity. This is exactly what I wrote here, because, as I mentioned, log b a is log a divided by log b. Of course, there are some usual speedups we need to use because there are still some unnecessarily complicated operations when the polynomials are. When this doesn't have such a nice constant as just a straightforward. We do use some sort of complicated operations, and if we want to compute this, then fast Fourier transform has an even worse constant. So if the polynomials have small degrees, then it's best to use just brute force. And when we in Karatsuba, when we recursively compute the polynomials of gradually smaller and smaller degrees, always halved, then if we've reached some case where the polynomials we are multiplying here are with sufficiently small degrees, maybe 20, 30 is the usual constant, then it's useful to just have an if in the implementation where if the degrees are small enough, then use brute force, otherwise use this recursive formula. There's still the question of whether when we computed C to n, that last number, whether we didn't spend too much time on it because we always need to do it when this result in these halved polynomials are odd. Fortunately, there's no problem with this because in each two steps we get from polynomials with some degree to polynomials with at most half the degree. That's because if we do this operation, then we definitely add odd degree polynomials, then we have even degree polynomials for which we need to compute the coefficients. And for those even degree polynomials, we already get two polynomials in the next step, in the next recursive step, which have half the degrees. So in every two recursive steps, we get to at least half a small degree of the resulting polynomials. So the number of steps we need to make like this is just log n. Oh, here is the Fourier transform formulas. This is a similar idea as with that fast multiplication of integers modulo some number. The classic algorithm where we want to compute a to the power of e, and if e is odd, then we compute a times a to the power of e minus 1, and if e is even, then we compute a to the power of e half and take its square, modulo some any mod. And this is computed recursively, this is computed recursively, and then there is just one multiplication. It's the same idea here. The number of times we need to do an operation like this, which is equivalent to this, is just comparable to the time we spent on doing these operations. To computing these coefficients is equivalent to computing the half power, and then the multiplications are equivalent to just computing the square. Actually, when we have Fourier transform, we can use something very similar if we need a lot of Fourier transforms, a lot of convolutions that are basically multiplying by the same thing. Originally, I showed something that was multiplication of 0 to n and b0 to n. What if we need to do something that take array A, array B, take their convolution, then take the result and convolution with array B again, then take the result of that and convolution with B again. Let's write this as let's use this asterisk to denote convolution. So what I'm talking about is A convolution B, convolution B, convolution B, etc. As I mentioned, convolution is commutative and associative, so it doesn't matter in which order we perform these operations. And the point of how to compute this is to take the Fourier transform of A, Fourier transform of B, and then as I mentioned, the convolution theorem that if we Fourier transform this formula, then we get this formula where the scalar multiplication is just multiplying the elements with the same indices in these arrays. Then in the same way, if we apply Fourier transform to this formula, then we get this. This is just scalar multiplication again. And since we don't mix indices in scalar multiplication, unlike in convolution, then this is just the I element of this is just well, when we take the ith element of this resulting array, then it's just the multiplication of ith elements of B of B of B etc. So if there are E such multiplications or E such convolutions after each other, then we can see that what we need to compute is just the modular exponentiation or whatever exponentiation we need of B, of each element of B, then multiplying by the corresponding elements of A. Then we get the elements of this, and we only need to use the inverse Fourier transform to get this. This is also quite common. Another way to use Fourier transforms is to, instead of having a formula like this, where there are two arrays whose elements we know, and we need to get an array whose elements we don't know, but which can be computed in brute force in a slow way, or using FFT or Karatsuba in a fast way. Instead of this, what do we have? A formula like C0 is some number which we know. A0 through something are also numbers which we know, or A1 through something, because A0 has to be 0. We can't have it as a normal number. Note that here we had j equal to 0, here we have j equal to 1, because if j is equal to 0 here, then we have ci here and ci here, which doesn't make sense. This would be just a formula to compute ci using ci minus 1. This we know, C0 we know, and we need to compute C1, C2, etc. Of course, this formula doesn't work directly because we don't have two known quantities here, but only one, and the other needs to be computed gradually and then used to compute the rest of these elements of array C. But we can still use a modified version of Fourier transform, modified version of convolution to compute this in some slower complexity using a divide and conquer algorithm. So let's say we have computed, let's 0 to n minus 1, or 2n minus 1 to keep numbers nice. Let's say we to n minus 1, so the first half of these coefficients. And we need to compute Cn through 2n minus 1. So if we take this formula, we can split it into four. I minus n aj. So we take the last n elements of this for j equal to I minus n plus 1 through I. The number of these elements is I minus n plus 1 plus 1. So this is n. And the remaining I minus n elements. The thing to notice is that this, which one? In this formula, we already know Ci minus j, all of them, because we've computed them here. We assume we've computed them already. That's because if j is at least I minus n plus 1, then I minus j, which is the coefficient of this, I minus n plus 1, which is n minus 1. These are exactly the coefficients we've computed. And, well, in this formula, we know this, and it is a convolution. It still is a convolution, and we can compute it using, just like we did in this formula. So, this is done. We, of course, as this formula works I at the same time, then it's when we compute the convolution here, then it's the same as computing this sum for each I greater or equal to n at the same time, and the remaining thing is to compute this sum for each I greater or equal to n. And well, it's the same thing as here. We can just do it recursively. This is already known. We just these starting sums, treat Cn, which is for which it's I minus n is 0, so this sum is 0, so we already know Cn just from this sum. Treat this as C0, Cn plus 1 as C1, etc. And the same formula applies here. Which time is it? I still have plenty of time. Also, there are some ways in which Fourier transform can be used, even if it's not completely obvious at the beginning. For example, if we want a convolution with binomial coefficients, so if a0 through n minus 1 are just some arbitrary numbers, and b0 through n minus 1 are binomial coefficients with some suitable power. Sums like this one. It's not completely obvious at the beginning that we can use convolutions here, but if we use the definition of binomial coefficients, which is that I over j is I factorial divided by j factorial times I minus j factorial, then we can group aj and j factorial together. We can take I factorial out, or just divide by I factorial, and then we have Ci divided by I factorial j factorial times I minus j factorial. This corresponds to this. Aj divided by j factorial corresponds to aj, and 1 divided by I minus j factorial corresponds to b I minus j. We can just read this as array A, array B, and to use the same formula like here to compute this sum. Alternatively, we could have, instead of aj, we could have cj, have j go from 0 to I minus 1, which would make this formula the same as this, where aj are 1 divided by j factorial. And then there is one more way to use convolutions that I wanted to show, which is what if we don't have a nice sum with independent indices like this, but what if we have some weird constraint, like in this sum, if we had a constraint that we are only summing up over j less than or e minus j. So here we would have I divided by 2, where this is integer division. The problem here is that there are some strange if you wanted to write this using Fourier transforms like I wrote before, where we have multiplication by omega, then there would be some cases where omega has to be 0 or something. It's quite weird, quite complicated. And in this case, we still can use a divide and conquer algorithm like I showed for this. How did it work? So we have two arrays. I illustrated it for myself like this, that we have two arrays and we split them in half. When we want to compute an element of their convolution with this special rule that this index has to be less than or equal to this index, then we take, for example, here and stop. So instead of just multiplying these pairs all the way, and if we are multiplying just numbers where I split the arrays into halves, where if we're multiplying numbers that one of them is in one half, the other is in the other half, then it's no problem. It's just a standard multiplication of pairs and adding them. And if we're multiplying numbers that are in the same half, from this half and from this half, then we can do it recursively. Again, using this form, this array into two halves, this array into two halves, and this subarray into two, this subarray into two, and recursively computing the product from pairs where one number is here, one number is here, and using convolution for it, and then recursively again on this and on this. mathematically I could write it as where in addition to these rules that J is less, we use a stronger rule where J is less than n. The arrays are again with indices 0 to n minus 1. So J less than n is aj from the left half of array A. B I minus j is from the right half of array B. Because I minus j is at least n. We compute these sums, and then we need to add all those terms where j is less than n and b minus j, I minus j is less than n. Plus the same for j and I minus j greater or equal to n. We compute this recursively. This is recursively computed. This is this sum, the same as this, is recursively computed, and in this case we don't need the special rule that j is less than or equal to I minus j, because it's already satisfied by this. This is basically just the convolution of the first half of array A and the second half of array B. It was in some encoder problem. I remember that it was. I tried to solve that problem using this in O n log squared n, because of course if we're using divide and conquer that splits an array into two halves and does something for them, and then the resulting computations that merge it and compute this are in O n log n using convolutions, using fast Fourier transform. Then it's n log n where log squared n where one log comes from the Fourier transform and the other log comes from the divide and conquer algorithm. Well, I tried to do it using this, but it was too slow and there was a better, faster algorithm, so it wasn't actually useful in solving the problem, but it's a good technique, which illustrates that Fourier transform can be used in many ways, especially with these divide and conquer algorithms, because I showed 2 or 3 of them here. Okay, let's have a short break here, maybe 10 minutes. 11:03, so till 11:15 let's have a break. I'll go in the whiteboard. quite simple but tangential topic of polynomial interpolation. The point is that sometimes we have problems with just two parameters given, or where just two parameters are relevant. For example, n up to 10 power 9 and k up to 1000, where one parameter is much larger than the other one, and we want to compute the number of something with these two parameters. If what's denoted by C and K, if the way to compute this C for small n is sufficiently simple and uses convolutions or polynomial multiplications or something like that, then it's very likely that polynomial in n is for fixed n, for fixed k it's a polynomial in n. Even if it's not obvious, even if it isn't clear that there are some convolutions or something that's used there, we can always guess that if one parameter is very small, the other is much larger, and then it's quite possible that the result will be a polynomial like this, and we can use polynomial interpolation, just compute ck 0 through k minus 1 if this is a polynomial of degree k. If it's a polynomial of a higher degree, it's usually comparable to k. For example, if degree 2k, then 0 through 2k minus 1 etc. And when we have these OK values, then we can use them to reconstruct the polynomial ck for all n and just evaluate it for the given n. In general, polynomial interpolation takes a polynomial like this, px with such that we don't know the polynomial, but we know that p xi equals yi for each I from 0 to n minus 1. So we have a polynomial with n with degree n, and it should be evaluated in at least n points. If it's evaluated in more than n points, then it doesn't matter, because either it's not if it is a valid polynomial, then we can just take n of these numbers and n of these pairs xi, yi, and use them to reconstruct the polynomial, and the rest of these pairs will fit that polynomial, or it's not a valid polynomial. So if we had more values, it's just useful for checking if we're really dealing with a polynomial. If we have these pairs, then we can use a formula like this. It's called Lagrange interpolation. Sum over all I from 0 to n minus 1 of yi times something that this number should be for x equal to xi, it should be equal to 1, and for any other x equal to xj, where j doesn't equal to I, it should be different. It should be 0, so that this sum would always sum up to the correct number. And how to choose it is is the product of x minus x divided by the product of xi minus xj, where the product is taken over all j different from I. So for a fixed term in this sum, for a fixed I, the products are for j from 0 to n minus 1, where we just skip over j equal to I, because if we didn't, then we'd have division by 0 at the bottom. Of course, all xi have to be different, because the same xi expecting different yi. So why this formula? Obviously, if we take x equal to xi, then this term will be 1, as we demanded. And if we take x equal to xk, where k doesn't equal I, then this doesn't matter, it's just a constant, and this will always have xk minus xj, where the product goes over all j except j equal to I, but k doesn't equal to I. So there is a j in this product such that we have xk minus xk for j equal to k. And so this product will be 0. So we have what we wanted. If x is equal to xi, then this is 1, and in this big sum, the only non-zero term will be the one where will be the one with yi for x equal to xi, then the only term that is non-zero will be the one with yi. And for this term, this will be 1. So the result is always that the polynomial given by this formula satisfies exactly all these equations. How to compute this, or how long does it take to compute this formula? Well, we have the products can be computed in linear time. This sum is therefore quadratic in n. This is O in total On. On squared in total, and of course we have these numbers with which we have to divide. There's something I haven't mentioned, but it's also quite common in programming competitions, that we have how is it called, multiplicative inverse modulo sum prime, where a to the power of p minus 1 is equal to 1 modulo prime p. This is known as Fermat's little theorem, and it can be used in this way. If we divide this whole thing by a, then a to the power of p minus 2 is the same as 1 divided by a. Since we can compute a to the power of p minus 2 using modular exponentiation, then it's simple to compute division by any number modulo this prime p. Of course, we need to have a GCD of a and p needs to be 1, or a needs to be coprime to p, which if p is prime, then any a between 1 and p minus 1 satisfies this. So we could compute all of these differences. If there isn't something to simplify these computations, like that these xi are sufficiently small. For example, if xi equals I, if we just evaluate the polynomial in, like I expected here before, in 0, 1 through this n minus 1, then these numbers are sufficiently small. We can just pre-compute the modular inverses, multiplicative modular inverses of all numbers from what it is 0 through n minus 1, and just do it here. But if they aren't special like this, if they're somehow given externally, then we need to add log p for computing this. Every time we need, well, we need to compute this for all pairs ij. There is a slightly more general version of this Fermat's little theorem, which is Euler's theorem. It also says that to the power of phi n is equal to 1 mod n, where a is coprime to n, so GCD of a and n is 1, and phi n is the number of a's that are coprime to n, which if n is prime, then the number of these a's is there are all numbers from 1 to n minus 1, so this will be n minus 1, which is the same as the Fermat Fermat's little theorem, which I wrote here before. So if n is prime, then phi n is that prime minus 1. There is a somewhat more complicated modification of this polynomial interpolation problem, where we don't need to just compute one number. We don't need to just know this ck in n, but in n1, n2, n3 to nm, for example, or in x1 through xm. That's called multipoint evaluation. And if we don't need to have obtained this polynomial just by or it could be just found somehow using some more complex convolutions or just given. But let's say we have m comparable to 10 power 5, maybe 10 power 6, and also comparable to 10 power 5, maybe 10 power 6. Then evaluating p in 1x is O(n), so evaluating it in all x1 through m is O(n)m, which is too slow. We can't afford it and need something better. What we can do is take some new polynomials which are x minus x1, x minus x minus m half and x minus x m half plus 1 etc x minus xm. So the polynomial obtained, the polynomial with x1 through m half, the first half of these numbers as roots, and the second half of these numbers as roots. So these two polynomials. Now let's compute p modulo this. What will be its value in all of these numbers x1 through xm half? It will be the same as the value of p in these values, because if p minus r, p mod r, the remainder of polynomials can be brute force computed as taking this polynomial, let's say the m half or the degree of r is smaller than the degree of p, then we can find some constant such that p minus r times that constant has this coefficient at k equal to n equal to 0, and subtract it. So we subtract polynomial r multiplied by some constant from polynomial p, and obtain a polynomial with degree at most n minus 1, and repeatedly do this. In this way, in the end, we reach a situation where the polynomial we are modeling, modulo that r, is the degree of p is smaller than r in the end, and in this case we just don't need to do anything. So the result of this operation p mod r is a polynomial with degree at most degree smaller than the degree of r. Otherwise, we could always find some polynomial that find some number, multiply r by that number, and subtract from this mod and decrease the degree. This polynomial is also uniquely given. I won't prove it here, but it's kind of clear. It works the same as modulo in normal integers. It's just that these aren't numbers, these are arrays or polynomials. So we take p mod r is equal to some q, polynomial q. This means that px is equal to rx dx, where d is their quotient, their ratio, plus qx. Rx is the product of these things. So if we evaluate p in, for example, x1, then px1 is rx1 times dx1 plus qx1, and rx1 is x1 minus x1 times something, so it's 0 times something, so this term is 0 for any x from x1 to xm minus xm half. So what we have is that in xi is equal to q in xi in any I between 1 and m half. Why did we do this? The degree of q is m half, because it's a product of m half. M half polynomials of degree 1. And so the problem we are left with is to compute the value of q in m half at m half points, and we can do this recursively. Just like here we computed the value of p in m points, and p has a degree comparable to m, then here we have a polynomial with degree comparable to the number of points in which we have to compute it, just that degree and the number of points are half as much. So we can do this recursively. The same has to be done for this, that we compute, let's say this is Sx, we compute p modulo s, get a polynomial like this one that's equal to p in all x m half plus 1 through xm, and also evaluated recursively. The main question, therefore, is how to compute this fast. If we could compute the remainder of one polynomial after division by another polynomial in time comparable to the degree of the larger polynomial times some log, doesn't matter what kind of, maybe log squared, it doesn't really matter, then we have an algorithm for this with complexity O m log squared. M is the same if I write m or n here, because m and n are comparable. One log would be from this divide and conquer strategy, and the other log would probably be from computing this. If this was m log squared time, then this would be log to the power of 3, but it doesn't really matter. These are just logarithms. They aren't very important here. How to compute this is a topic I'll leave for later, because it's quite complicated and deals with completely different things than we've had so far. Then there is another thing with power series that I haven't really mentioned so far, because I've always dealt with just polynomials and series that have a finite number of coefficients. But what if we take this? This is not anymore a polynomial, it's just some function f x, and if ck are numbers representing some interesting sequence that has, for example, some number of ways to choose k things, then this is called the generating function of a sequence C. To compute it, since if these ck's are fixed and the sum actually looks normal, it actually if we actually compute the sum, then we get some function. It's we don't get it in infinity for some range of x. Then we can see that this function f is always differentiable. We can always take its derivatives, dx, for example, is equal to the sum of kck x to the power of k minus 1 for k equal to from 1 through infinity. K equal to 0 just disappeared because it was just a constant and derivatives of constants are 0. And so on. It's the 8th derivative of f by x is equal to a sum like this, where k is from a through infinity. And of course, if we take this as, for example, this as a function and set x equal to 0, then all terms with k greater than a, strictly greater than a, will be 0 to the power of some positive number, and it will be 0. And the only term left is the one where k equals a. So this evaluated in 0, in x equals 0, is ck times k factorial. This means we can obtain ck by k times differentiating f, taking the k by taking the kth derivative of f and dividing it by k factorial. We compute the number of ways to do something modulo some number, so dividing by k factorial is again using this formula or the simpler version with Euler's the modular exponentiation. There is one problem where this is very useful. It's we have some piles of A1 items, A2 items, etc. through n items, where n is small, for example, up to 20, and ai is up to 10 to the power of 18. All items in each pile are indistinguishable, so these A1 items are indistinguishable, these are indistinguishable, etc. And we want to compute the number of ways to choose a total of S items in total. So since the items are indistinguishable, then it's some where the number of ways to write a sum like this, which is equal to S. How do we do this? Because we could use some dynamic programming if these AI were sufficiently small, but they are so large there is no chance of doing it. The point is to express the number of ways to get S as this number. So ck will be the number of ways to get sum equal to k, or cs will be the number of ways to get sum equal to s. And notice that if we have this sum, then x to the power of s is x to the power of b1 times x to the power of b2 etc x to the power of bn. This product. So if we just took the number of ways to take this to take just one pile and pick k items from it, A1. It's this kind of function. Functions f1 times fn gives this function f that has ck as the number of ways to choose this sum. Notice that in this sum, the coefficient of x to the power of k is the number of ways to take just one pile with a1 objects and take k objects from it. And because if k is at most a1, then the number of ways to choose k indistinguishable objects is just 1. We just take k of them and we're done. And if k is greater than a1, then there is no way to take more than a1 of them. And if we multiply it, then then basically we have with this sum we have all ways to choose these numbers b1 through bn. And as we multiply these functions, it just gives us the number of ways to make this sum. So the k coefficient of this function as a power series is the number of ways to make this sum. The question is how to compute it. Of course, this is just a geometric series. It's simple to see that this is 1 minus x to the power of a1 plus 1 divided by y minus x. So this f is equal to the product of 1 minus x ak plus 1 divided by 1 minus x to the power of n. This is just the product of the top in terms of the numerator, the product of the denominators. Of course, the product of the numerators is easy to compute because it's just a polynomial. There are two terms in each of those simple polynomials we are multiplying, so this can be computed in O2 to the power of n. It has O2 to the power of n terms. This is why n had to be up to 20. or up to something sufficiently small. The question is what to do with this, because as I described, we need to find CS, and it can be only be found by computing the derivatives of f, and we need to compute the derivatives of this. It's not so simple. If I take 1 minus x to the power of minus n, which is just this denominator with power of minus n instead of dividing by it, and want to take its derivative, then this is minus n times 1 minus x to the power of minus n minus 1 times minus 1 as the derivative of the inner function. I don't know if you had derivatives or if you work with it, but if you haven't, just well, trust me. So this is just n times something that looks very similar, just the exponent decreased by 1. And if we take, if we do the same operation, this derivative, if we apply the derivative to this multiple times, then what happens is just that we get n times n plus 1 times n plus a minus 1. If we applied it a times, times 1 minus x to the power of minus n minus a. Of course, we want this in x equal to 0. So this becomes 1 when we take x equal to 0, and we are left with n plus a minus 1 factorial divided by n minus 1 factorial. So these are basically the coefficients of 1 minus x to the power of n as a series. We actually want to just compute the coefficient CS. So we have this polynomial, and let's denote it again by px, and this by qx. Is the same notation as I used here and before, but it's just completely unrelated, just unrelated polynomials. So what we want to compute is in this in the product of 1 divided by q. Right, I have to divide by a factorial here to get the correct coefficients of this series. This is a polynomial, this is a series, not an actual polynomial, just a function. So we want, we have
isn't it a factorial QA?
Yes, a factorial, and this is the formula for QA, which is the 8th coefficient of this series Q. So what we want to compute is the sum of or the series of Q to the power of minus 1. P s minus a, and this is equal to that CS, which is the number of ways to make the sum we're looking for, or the coefficient of this whole function f. Which is p divided by q. This is p, this is q. We know the coefficients of this. S may be large, but the number of coefficients which are non-zero is just O to the power of n. So we can take all these coefficients. For each of them, we can compute. We can find out which index it has, compute which index this needs to have. So we know for which a we need to evaluate this coefficient. Evaluate this factorial, this factorial, this factorial. It can be done in, actually this whole binomial coefficient can be evaluated in On. If okay, this can be this divided by this can be this divided by this can be evaluated in On by just taking no.
N is little, is small, and A is big. So you just go like. Okay.
All right. This is a times a plus 1 times a plus 2 times a plus 3 etc. And this is n minus 1 is separate. We can evaluate this easily since n is small, and then we have since this is divided by a, it's a plus n minus 1 and a plus n minus 2 etc. through n a plus 3, a plus 2, a plus 1, and the rest is already divided here. So this can also be evaluated in On time, and the resulting algorithm should have something like n times 2 and 2 to the power of n complexity. Because of course we didn't try to evaluate many coefficients of this Q, but only find out which coefficients are non-zero for P, and for each of them find A, and for a given A we can compute each coefficient in On. So we needed to use this power series. In this formula. I'd like to show this way to compute one polynomial modulo another polynomial. which is also tied to how to compute an inverse of a polynomial, which is the general form of what I showed for this 1 minus x to the power of n. So I'll go in this. Let's take a polynomial px. And what we want to compute is a polynomial, is a pair Rx and this will be G and Rx and Qx such that so this is the formula for polynomial remainder. This is the remainder, this is the quotient, and P modulo G, which is R, polynomial R. Let's take a reverse. Let's reverse these polynomials. Also, let's assume that C n is equal to 1 and D m is equal to 1. If they aren't, it's just a question of dividing the polynomials by sufficiently large constants, which should always be possible if we work with polynomials like this. So let's take an inverse polynomial, reverse of P, which is the sum of C n minus k times x to the power of k. So it's 1 plus C n minus 1x plus etc. In the same way, let's take a reverse polynomial G and the reverse polynomial Q. If it's true that if we have two polynomials, let's name them p times r equals s, then if multiplying two polynomials gives us a third polynomial, then multiplying the reverses also gives us the reverse of the third polynomial. This can be proven quite easily if you just write the formulas. It's basically that reversing is just multiplying by some power of x. And reordering coefficients then. The point of this reversing is that we have reverse of p equal to the reverse of gq plus r, which is equal to plus the reverse of r times x to the power of degree of p minus degree of r. It should be like this. Of course, the reverse is additive for two polynomials with the same degree. So if we have r should have a degree smaller than the degree of g, we need to add some zeros at the end of its coefficients, so we would have a polynomial with degree n from r. And if we reverse this polynomial, then there are at least the degree of p minus degree of r zeros at the end, which got moved to the beginning. So the first, these many coefficients are 0, and the rest are the reverse coefficients of r. And we have this formula. Now the thing to notice is that the degree of r is smaller than the degree of g. So if we take this formula modulo x to the power of deg p minus deg g. So if we just discard all coefficients with where all powers of x and their coefficients where the index like k here is greater or equal to the degree of p minus degree of g, so n minus m. Then since the degree of r is smaller than the degree of g, this power of x is greater than this, and this means we can discard everything here. So modulo this, if we discard all coefficients greater than this, then we are only left with this modulo. Reverse of q. this is useful because if we know p, we can compute the reverse of p, we can discard all coefficients up to n minus m. Then we know g, we can compute the reverse of g, also do the same thing with it modulo, and then we are left with computing the reverse of q. Q is the quotient, the ratio of these two polynomials, so the degree of q will be at most n minus m. This should be.
Question,
Yes.
pretty silly. How do you know that when you take the modulo operation, you won't change the value of rev g, rev q?
The value of rev g and rev q changes, but it doesn't matter. If we work modulo this, the point is that we want q, and q is well, q should have degree up to n minus m. I think this should be plus 1, or not sure.
Oh, okay. Otherwise,
Yes,
Otherwise, q times g won't be p.
plus 1. So even if we do plus 1 here, since the degree of r is strictly smaller, then this will always be 0 modulo this. And we know that we want the reverse of q modulo x to the power of n minus m plus 1, which gives us the first n minus m coefficients of this polynomial q. But we know that polynomial q will only have n minus m coefficients because it's polynomial with degree n divided by polynomial with degree m. That's not a problem. The point is that exactly that we are only computing a polynomial modulo something, but we know that this polynomial will be the same modulo something as not modulo.
Thank you.
No problem. Still we are left, which is that to compute the reverse of q, we need to take reverse of p times reverse of g inverted. This is a polynomial multiplication. It's classic, but we need to compute the reverse of g modulo to this. X to the power of n minus m plus 1. So the first two coefficients up to x power n minus m. Reverse of g inverted modulo this. This is a polynomial since g had the first coefficient equal to 1, then this should be a polynomial such that reverse of g times as denoted by h. Its first coefficient should also be 1, and h1x2 h n minus m x to the power of n minus m. This should be equal to 1 modulo x to the power of n minus m. And we need to compute this polynomial. This is an even more difficult thing. I'll need notes for it. this inverse polynomial is computed by gradually taking it modulo x to the power of 1, x to the power of 2, x to the power of 4, etc. Always x to the power of some power of 2. Of course, it's not a problem if we computed modulo x to a larger power than this n minus n plus 1. It's not a problem because this modulo is just discarding all coefficients larger than something, and if we discard less coefficients, then nothing bad happens. Now we need to know how to take a polynomial ax such that hx times equals 1 modulo x to the power of L, and get some polynomial equal to ax plus x to the power of L times cx such that hx times bx is equal to 1 modulo x to the power of 2L. Of course, A just forms the first L coefficients of B, and C is some polynomial which should form the other L coefficients of B. So if we evaluate this, if we write plus x to the power of L times h1, so again we split h into h0 with the first L coefficients and h1 with the next L coefficients, then this is h0 times a plus h0 x to the power of LC plus x to the power of LH1 plus x to the power of 2LH1C modulo x to the power of 2L. Of course, since we're taking this modulo x to the power of 2L, then this is equal to 0, because it's x to the power of 2L times some polynomial, whose first two L coefficients must be 0. H0A is equal to, well, its first L coefficients will definitely give something equal to 1, and then there is some other part, so we can write H0A as 1 plus x to the power of L times d, where d is again another polynomial. So this is is 1 plus x to the power of L times d plus h0c plus h1a. We can compute h0 since it's just h is just a polynomial for which we need to compute the inverse. h0, h1 are therefore known. h0a is also known because a is something we've already computed. It's the first L coefficients of the inverse. So we know h0a. So we can compute this, subtract 1 divided by x to the power of L and get d. So h0 is known, h1 is known, d is known, a is known. And we know that this is equal to 1 modulo x to the power of 2L. So this is 1, this is x to the power of L times something. So this has to be equal to 0 modulo to x to the power of L. This thing has to be equal to 0. So we know from this we know that C, which should be the thing we need to compute, the other L coefficients of the inverse, C is equal to minus d plus h1a divided by h0. And the inverse of h0 should be a. Yes. This is on modulo x to the power of L. h0 dividing by h0 is the same as multiplying by a, so this is a times d plus h1a. And this formula gives us from L coefficients, which are in A, L coefficients of the inverse of h, gives us the next L coefficients of the inverse of A, of h as this, which is something that can be computed if we know how to multiply polynomials, which I've shown just at the beginning using Fourier transformation and multiplication, addition of. What's the time complexity of this? Well, we always take some power of 2 of coefficients and then compute twice as many coefficients from it. So the number of steps we need in this is log, and the time we need for each computation is the max degree. That's bounded by the max degree of the initial polynomial, so n times log. So the inverse of h can be computed in O n log squared n time, where n is the let's say the degree of the original polynomial we are inverting, so the polynomial h. The time is roughly up, and there is still one thing I wanted to show at the beginning. It's not very important, but well, it's just why Fourier transform works. The case with discrete Fourier transform is actually quite much simpler than it is with continuous Fourier transform, because there we need to use some integral theorems, but with discrete Fourier transform it's just classic simplifications of sums. So we have a I equal to sum like this. The same for B and for C. And then we have Ci is equal to the sum of omega to the power j, and now I'll write Cj as this sum aka b j minus k. This is j0 through n minus 1. This is k0 through j. So this is the formula for the Fourier transformed convolution of A and B. And if we switch the sums, then it becomes sum over k is 0 to n minus 1. AK can be moved outside. Sum through j equal to k through n minus 1. It becomes this sum. And if we take AIBI, then this is with suitable naming of indices BL. So if we rename here M plus L M plus L is equal to J, then this is equal to A to the power of M sum over J omega to the power of minus ij BL, where L is J minus M. This is from 0 to n minus 1. J is from L equals 0 to M. It's sufficient to take it somewhat smaller, up to n minus 1. Since m is from 0, then j is from L. Omega to the power of im, omega to the power of minus il, add up to omega to the power of minus I m plus L, where m plus L is equal to j, so it's this term. It comes from these two. Am was just rewritten here, and bl is bj minus m. And you can see that we actually arrived at the same formulas. It's just that here we had k and here m, and here k and here L. J equal to, right. M. K was renamed to m and j remained. It's actually the same formula if you compare it. So we have AIBI equal to CI. So I guess the time is roughly up. It's enough to end here. Thank you for your attention. Hopefully it wasn't too confusing for you. And we'll have a contest in the afternoon.
Thank you.